oh, there we go. This is a project that is actually finished now. We're running for 4 years, EPSSE funded, and it was in collaboration with Cardiff and Queen Mary University. It's got quite a long title there for papers and the like, but the main thing was that the main amount of money actually went to Queen Mary, because the guys there, and Graham's just sitting at the front there, were developing this huge new X-ray scanner, and the whole point of it was that we were going to be able to scan very fragile documents, in particular scrolls. And so this is the Dead Sea Scrolls. Now, we didn't have any Dead Sea Scrolls, although we wish we did have some, but it gives you an idea of the problem. So they have these scrolls that are very, very delicate, all rolled up, and then when they try to unroll them, they literally fall to pieces, and they turn into little fragments, and then they try to stick them together. In the old days, they used sellotape and just stuck it all together, but that's not really the best way to do it. So the idea was, maybe what we could do is stick it in an X-ray scanner, high resolution, and then without actually unrolling it, we could do a sort of virtual unrolling to see what's written inside the scroll. So I'm not going to give you any of the details of how we actually went about and did it. We've got a pipeline there that we developed over the years, but the bottom line is that we actually ended up being able to develop something that did work quite well. So here's an old scroll from 500-600 years ago, and it's unrolled partially here, but that's as much as you can unroll it. After that, it's stuck together, because these scrolls, when they get a little bit damp, also heat and so on can affect it, and it gets them sticky, and they get glued together. So that's what the scroll looks like, and that's what we can see, but the target then was to be able to read what else was hidden away inside that scroll. And so the result of a lot of work, as I say, it was a bit of a rush at the end as the project was terminating, was to generate this. So this is the whole scroll. You can't really see it terribly well. Sorry, I say this is the whole scroll. This is the whole scroll that we managed to unroll. There's actually another section here that we couldn't manage just because the quality of the geometry of the scroll itself was so degraded and complex that our algorithm couldn't quite cope with it. And moreover, in any case, you can see that the contrast here is getting quite poor. So what we have is that the ink has a high contrast and therefore can be detected and projected onto this 2D view of it all. There's a close-up which you can get a better feel for what's going on there. So you can see that we can really get some high-resolution text out there. This is, of course, Old English, so it might look a little bit strange to you. But nonetheless, it was sufficient for the archivists to be able to read that and to find out some quite interesting things about what was going on there in the old days. So this is actually just a manorial sort of list of rights, things like fishing rights and so on, that were granted by the owner of the lands. So you can see very high resolution. And as I say, that all worked out quite well. And we had a little item on the one show at the end of, well, it was filmed at the end of last year, broadcast this year. So that was quite a nice little project. I'm just jumping there to give you a sort of glimpse of it. And if anyone's interested, you can certainly ask me about it later on. But let me move over to this one here, which is what I'm really meant to be talking about, which is non-photorealistic rendering of images. So something rather different. And this is mostly work that's been done with my colleague, Yu-Kun Lai, also at Cardiff University. And the plan was, I thought I'll go over, quite overview style, a few of the things that we've done over the years. And then to give you maybe a little bit more technical stuff, I'll go into some of the details of the pipeline on just one of these techniques towards the end. And depending on how I do for time, I may have to sort of speed that up and miss out some of the stuff. So if you can just keep an eye on the clock and tell me when to stop, so I can stop any time, as it were. So just to maybe make clear what this is not about, it's not about photorealistic computer graphics. There's lots of stuff out there and trying to generate very realistic looking views, but this is about non-photorealistic rendering. It's also not quite about computer art in a sense. There's quite a lot of stuff out there on computer-generated art where we actually try to have some sort of creativity in the computer. And maybe the best known one is this Aaron system developed over the last 30-odd years by Harold Cohen. And he generates, this Aaron computer system generates some quite pretty looking, quite abstract, but not always abstract art. And here are some examples. I would say actually to me, they all look a bit of a muchness. They all look rather similar, but nonetheless they are quite pretty. But we're not talking about that. What we're actually on about is taking an image, so this is all image-based, although you can get 3D sort of mesh model type approaches, but this is all image-based where we take an image as input. So here's an example, standard image, apply some sort of algorithms to generate what's called a non-photorealistic rendering of it, which is meant to be something more artistic. Although that's a somewhat vague term in terms of what does artistic or aesthetic really mean. And so you can imagine there could be many possible applications. I mean, nowadays you get hundreds of apps which can do this sort of thing. You can generate re-rendered versions of images or photographs in different styles. You can have it in cartoon style. You can have it in impressionist style, post-impressionist style, stippling, all sorts of different techniques. So we're going to look at a little bit at how we can do that. Also, there's been a take-up here. For instance, there's been a bunch of films, this is probably the best known, which also created a sort of slightly cartoonized non-photorealistic rendering. So there's a whole feature film done in this style. Now, as far as I know, this was done somewhat manually, or at least semi-automatically, because there's quite a challenge, quite a technical challenge to do this sort of rendering, and in particular for a film, to be able to ensure some sort of temporal coherence. Because if you're just to analyze and re-render every frame independently, put it all together to create a video, it's going to look really horrible. There'll be all sorts of flickering going on there. So in actual fact, they did a lot of this manually, and they used just standard old-fashioned techniques developed by Disney back in the 1940s or 50s, rotoscoping, so a sort of manual overlay to actually generate something like this. But there are some maybe more useful set of applications which aren't just about entertainment. So one of them is scientific illustration. So in this example here, it's actually starting off with a 3D model rather than an image. But the idea here is that we can re-render that 3D model in various ways to make it easier to understand. So you've probably all come across illustrations in manuals. In the old days, they'd be carefully drawn out by some artist, a draftsman. More recently in times, they just take photographs because it's cheaper and easier. But it doesn't necessarily mean it's actually easy to understand what the photograph's all about. So here, they've highlighted boundaries, and they've given various indications on the three-dimensional shape there, and they can get something that, you probably agree that this is much easier to understand the geometric nature of what the object is than a more photorealistic style. So that's one possibility for NPR. Here's another one, which is actually one that we did at Cardiff a year or two ago, which was we've got a project, another EPSSE project, on bas-relief generation, and that's involving shape from shading. So the idea is you start off with an image, and then use shape from shading, which can then generate from the intensities in the image a three-dimensional surface. And then once you have that three-dimensional surface, then you can create a bas-relief by doing some sort of non-linear mapping on the heights to compress it down. But it's got to be non-linear, because if you want to make it compress down like a coin, where the head on the coin is very, very shallow, the depth, it's only maybe a millimeter or less. And if you just do a simple linear compression, then what will happen is you'll end up with something that looks totally featureless. So you want to emphasize things like the nose and so on, and you can sort of minimize any variations on fairly smooth surfaces like that. And so what we found was that if we took our input image and then applied our non-photorealistic rendering method to it to create something like this, what it's actually doing is it's emphasizing various salient aspects. So it's pulling out the edges, making them stronger. It's reducing the variability in places where maybe it's not so important. So you can see that the highlights and so on here have all been flattened out. And then what we found was that when we then apply our shape from shading and the nonlinear compression, we get much more attractive, at least perceptually attractive looking results, as shown in this column here, than without the NPR. So as I say, there are various applications of NPR, but that's not really my motivating factor. It's really just doing it because it's quite fun. So here's another one which is quite fun, and this song here will recognize because he generated these images, I think. Did you? Yes.
But only famous work, yeah.
And here, the idea here was to apply a non-photorealistic rendering that was really quite extreme in a sense. We were doing some extreme abstraction so that we could end up with a representation of this image in various styles, which, like a real artist like Picasso or whatever it is, we would maybe capture some intrinsic element from the original, but it would look quite different. So obviously here you can see there's a lot of geometric stuff going on, so that's relating back to what Song was talking about before. I'm quite keen on shape analysis, and have done a lot of work on fitting shapes like triangles and rectangles and super ellipses and all sorts of things so that we can stylize the element. So in a sense, what we have to do is we have to break down or decompose the image into components, into regions, in this case, and then we can re-stylize these components in various ways and re-render it in a whole variety of manners. So here's the next approach, and this is actually the one that I'm going to spend most time on. So what I'll do is I'll just skip over it now, and then we'll come back to it later on when I go through all the elements in the pipeline. But this was a technique which was following on from that work with Song on the stylization. We still wanted it to be what we called a minimal stylization. We didn't want lots and lots of detail. So there's a lot of NPR work there, which is all about rendering with various graphical primitives, like strokes or stipples or whatever it is, where you can have hundreds and thousands of these strokes or whatever to build up an image, supposedly like an artist would do, with doing lots and lots of strokes. But you can get something at the end that is quite realistic only by virtue of having all these strokes. So there's not terribly much abstraction going on, whereas here we wanted to really keep it minimal, really keep it basic. But then there's a bit of a problem, because when you've got hundreds and thousands of strokes, then if you've got a few strokes that are wrong, you don't really notice, because it can all be hidden away by all the other strokes. If you're boiling it down to just a small number of graphical elements, then any mistakes can be really quite critical. So we wanted to be minimal, that was the first thing, but we didn't want to go quite as far as Song's work, that we wanted to still somehow retain enough detail so that we could actually, for instance, recognize a face. So hopefully you can all recognize this as Spock, even though it's stylized. So it's stylized, but not quite so extremely stylized. Well, that was one bit of work. And then that led on to another piece, which was we'd gone from the original image down to something that was only black, white, and gray. And then we thought, well, let's add a little bit more color back in. Let's add a spot of color. So we had this bit of work on spot color, which is a term which relates to just having a single color added into the image in a place. And so I'm only going to show you this one slide, but I'll just give you a brief overview of the sort of things that were involved. So what we had to do was take all the colors in the original image and consider different subsets of these colors. And we tried a few different approaches. So one approach is to use something called universal colors. So some of you are probably familiar with face analysis, because I know it's quite popular here. And so with face analysis, you're probably familiar then with the Ekman idea of universal expressions, where you've got these 6 universal expressions, universal across all cultures in the world. Well, around the same time in the 60s, as Ekman was doing his facial expression stuff, there were 2 guys, Berlin and Kay, looking at colors across cultures around the world. And they found that there were 11 basic colors that didn't matter really where you came from. These were likely to be the colors that you'd know. And they were the colors of the rainbow: red, orange, yellow, green, blue. Indigo and violet was just purple. And then pink, brown, black, white, and gray. So these were the 11 universal colors. So we can use these 11 universal colors. We can map them out by human perceptual experiments, and then break up this image into these color masks. And then the question is, which one are we going to choose? Which is the appropriate color to use for this image here? And the idea then is to use some spatial information. And so we would say that, for instance, we might expect that the region of color should be quite compact. So we used a measure of compactness to rank the various color masks. And as well as that, we'd also say, well, it'd be sensible to have that color in somewhere that's important, that's salient. So we use some salience detection as well to combine with the shape, and that's what we end up with. And once we've got our color, we can then combine it with various NPR styles. So we can render it this way, which is our method, or we can render it in a sort of pencil style or whatever you like. Well, that color thing also led us on to thinking about how we can break up an image into a set of discrete colors. And that actually led us on to looking at thresholding algorithms. If we were to consider the color channel, so if we were to take an image, color image like this, which could be represented by its red, green, and blue components, and then if we project it into a different color space, in this case here, hue, saturation, intensity color space, once we have the hue, we could then break up that hue into a set of discrete hue classes. So a bit like using the Berlin K universal colors, but this is a more data-driven approach. And so we started looking at thresholding algorithms. And we're looking specifically at something called Otsu's algorithm, which is a very famous algorithm which takes a histogram, splits it up into 2 or more classes, and then chooses the splitting point, the threshold point that maximizes the inter-class separation and minimizes the intra-class separation or variance. But the trouble is that when we're looking at hue is a circular quantity. It's like a color wheel. So it makes it a little bit more tricky to apply Otsu's algorithm. So we started looking at that, and that was a sort of spin-off that led us to quite a nice paper that just came out recently in IEEE image processing. And what we found was that rather counterintuitively, if you apply that Otsu's algorithm to a circular property for the 2-class case, what you find is that the 2 classes are always equal in size. Now, it doesn't really seem obvious that it should be like that, but we proved that it was. And what this means, therefore, is that you can actually much more efficiently compute the threshold because you've only got 1 variable to play with instead of 2 variables if it's a 2-class problem. Whereas in the past, people quite often approximated this threshold. We could actually now do it optimally and efficiently. And so that was one spin-off from this. And then also we thought, right, we've got all this thresholding stuff. Let's now apply our thresholding to our image in this hue saturation intensity space, or sorry, hue saturation value space we used at the end of the day. And if we do a 3-class thresholding of these 3 components and then recomposite the components back again into an RGB image, we end up with something like this. We've got some lines in there for good measure, like we had in the previous method. And you can see that, again, we're having quite a nice balance between something that's recognizable, but also something that's stylized. And we're actually still at work in this at the moment. And so I met Ricardo just a couple of weeks back where we're trying to demonstrate a video version of this. And it's still work in progress, as I say, because really we need to work a bit more on temporal stability, temporal coherence. But we can get some quite nice results. And in these videos, the identities of the actors are really quite recognizable because it's got enough detail there given by the lines, but enough abstraction given by the colored regions to give quite a nice aesthetic property. Okay, on to yet another paper. Now this one was motivated by the idea that a lot of NPR work is quite focused on local low-level properties, you know, different styles of stippling or different strokes and so on. And so the idea was to look at maybe something a little bit larger in scale. And in particular, we're influenced by a particular artist, a local artist, which had a lot of straight lines. They had these linear structures, and what they did was they used the linear structures to sort of combine together local evidence of linear objects, which could be separated across the image. So for instance, in this case here, we can see there's a bit of a line here, and then it's interrupted, but then it reoccurs over here. But these 2 bits of lines are co-linear, and therefore, you know, there's some evidence that there's a sort of larger scale structure, and then they just apply that larger scale structure to emphasize that in the image, and it looked quite nice. So we developed a technique which was trying to mimic that to some degree, where we had some Huff transform stuff to detect linear structures, and then once we actually had that, we could then apply a certain harmonic field which would then modify the colors in the regions so that it would emphasize these linear structures. And not only that, but we could, given these linear structures, we could then start doing some geometric distortions as well. So here, what we've done, again, following from this artist, is we've said if we've found some linear structures that are close to horizontal and vertical, let's just warp them and distort them to make them perfectly horizontal and vertical. So it may look a little bit odd, but it's just another way of stylizing images. Here's another one. I'm just going to go through this one quickly. This is just about, again, inspired by some art. It was actually an Agatha Christie book cover that I saw. They had used essentially an image like this, and then a shape like this, and then used another shape to fill in the hole in the first shape to generate something like this. So here, essentially, it was a little project actually done at Tsinghua University in China, where they did a lot of matching so they could match objects across different scales with rotations and translations and so on, and then recomposite shapes together to create these quite interesting patterns. We're essentially using a negative shape to fit a positive shape. Okay, I think this might be the last one, which is, again, some early work where we had some combination of images and depth maps, which allowed us to be able to do a little bit of manipulation. And again, we're stylizing these images or depth maps by finding edges in the intensity image, but then also, because we had the shape, we could of course render it from different views, but we could also do some geometric shape distortion. So here we've made the nose a bit bigger. So that was quite a fun little thing to do. Right, so now I'm going to have a go at describing that pipeline for one of the early methods I was telling you about, just to give you a feel for the sort of elements involved. And it's a bit of a sort of mixed bag where we just took whatever computer vision techniques we felt were necessary, threw them all in to the mixture to generate the results. So a lot of the techniques are not necessarily new, but we had to put them all together to get the results that we wanted. And so let me show you the inspiration. We started off being inspired by various artists. So Matisse, this is the famous snail painting here, highly stylized. This is somewhat similar to the arti-shape paper with Song. But also we wanted a bit more detail, so we were quite inspired by Picasso and the likes, Matisse, Matisse also did something like this. These line drawings where quite a sparse set of lines seems to capture a lot of information. So it's obviously recognizable in terms of its geometry, but also recognizable in terms of its identity. That's, I think that's Stravinsky there. And then we're inspired by Warhol, who took a sort of mix and match approach, if you like, where he took together photographs, bits of line drawings, scribbles, and just stuck it all together in this sort of style. And then a final inspiration, which was computer vision inspiration, was this paper by Kang on coherent line drawing. And he had this paper a few years ago where he demonstrated this technique for extracting out lines from images, which I thought was really excellent. It could do a very good job. If you were to compare this with some other standard simple line detectors or edge detectors, this really looks certainly much, much more artistic. He's really managed to capture the salient information and throw away a lot of the rubbish. So I'll mention a little bit about how he does that in a second. But the idea was we could put all these things together and come up with a NPR technique for image stylization. So I've got a pipeline there. It doesn't matter that it's small because you don't need to actually read it. It's just to show that there's quite a lot of steps in there, and I'm going to go through some of these steps here. So this is the Kang approach for finding out, for extracting lines from images, and it can do quite a good job. This one actually looks a little bit messy because the image is a bit noisy, but that was our starting point. So how does it work? Well, it's just a difference of Gaussian, which is a sort of approximation of a Laplacian of Gaussian, but his clever trick is in terms of the kernel. So the geometry of the kernel, instead of just having a standard square kernel or a circular kernel, what he does is he adapts his kernel on a pixel by pixel basis to the local image content. So what he does is, if you imagine this is a window in the image here, he computes this edge flow field. So he computes edges where there are strong edges, and then he propagates out, he computes edge orientations where there are strong edges, and then these get propagated out to create a dense flow field over the whole image. And then at a given point where he wants to apply the difference of Gaussian, what he does is he builds up the kernel by moving the kernel to align it with this edge flow field. And he does that at every single pixel. So every single pixel will have its own kernel geometry, and then within that kernel, it's essentially a standard difference of Gaussian that's just bent around the shape. And what that does is it prevents essentially things getting blurred or distorted across the edges, and it preserves the edges and the lines very nicely. So that's what he did. But if you go back to that previous image, it doesn't quite look right, maybe. You know, it's got some lines in there, but it's not really an appropriate representation for this image because it's thrown away, essentially, all the tonality. It's thrown away the dark and the light blocks in that image. So what we wanted to do is to bring that back in again by detecting these tonal blocks. And I'll describe how we do that, but essentially, that's what we came up with at the end of the day. But not only that, because once you've decomposed the image into these blocks, you can stylize them, like what we did with Song and the Art of Shapes. So we can change the geometry of the blocks, of the dark blocks and the light blocks. We can pattern them and do all sorts of stuff like that. So here's an example of this first element in the pipeline. We start off with the image. We can extract some lines using this difference of Gaussian. We apply some hysteresis, which is the same sort of technique used by Canny in his edge detector, which cleans up the results a bit. And we can do a little bit more mathematical morphology to do a bit more cleaning. And we can get something that looks pretty good. But we were also inspired by artists. Here's one by, can't remember, Leonardo, I think, or Albrecht Dürer. And what the artists often do is they combine not only the dark lines, but also highlights with some light lines. So here it's a mixture of charcoal and chalk. And it seemed that was very appropriate, that as well as extracting dark lines from the image, we should also be extracting light lines. And so we now imagine that we're actually drawing our lines on a canvas, which is mid-grey. So we've drawn on this grey canvas some black lines here, and also now you can see the light lines. And the light lines are picking up highlights and other sort of intensity illumination variations, which gives you a much more sort of three-dimensional feel for what this image is representing here. Just for comparison, here's a 3-level posterization or thresholding of the image. And it's not bad, but in some sense this maybe captures better the intrinsic important features in the image. But we'll put the tonal blocks, the dark and the light blocks, back in again at a later stage. In fact, here is how we do it. So in a sense, this is maybe the weak point of our algorithm. It's a classic computer vision problem, which is segmentation. But although people have been struggling with it for the last 30, 40 years, there's still not really a good solution. So we did our best. We used standard state-of-the-art techniques. So what we did was we started off with the image, or the intensity channel of the image, and we did a threshold into 4 classes. So we sort of visualize that we've got 4 classes, and then the bottom darkest class of intensity values are going to be definitely dark, and the lightest class is definitely light, and then we've got 2 middle classes in the middle that's sort of in between. So we're hoping that the bottom and the top class are going to be we're going to be pretty confident that they are dark and light. So here's the dark class of pixels, and we then do some morphological cleaning up to get rid of all the little bits and bobs. It also does a bit of distortion while it's at it, which isn't that great. So what we then do is a post-processing step using grab cut, where we initialize the grab cut with this here, and what it does is it refines the geometry of this region by incorporating the initial mask with the original data, and you can see it gets a very precise outline here. You can also change the topology while it's at it, which can be useful as well, but not always. So there we go. From the image, we've pulled out a dark region. Could be more than one dark region. It's just one in this example. And do the same thing in reverse, essentially, for the light region. So here we go. This is the original light region here, this white bit here. Bit of cleaning up, graph cut, and then that's it. So that's the region here, which of course doesn't really show up terribly well in the original image, but that's what came out of the thresholding. And then once we've got that, we can put it all together. So we've got our lines, dark and light. We've got our regions, dark and light. Stick them all together, and that essentially is our method there. Having said that, it's a little bit tricky, because if we've got black lines that we want to draw on top of a black region, what do we do? You might think black and black should be extra black, but we don't have an extra black color to use. So what we do is, it seems a bit counterintuitive, but we actually do a sort of inversion, which is also what artists do. So if you're trying to draw black and black, to make it visible, we draw it as grey. Not white, we keep it as close to black as possible, but we change it to grey so it's visible. So we've got a little table here of all the possible combinations of different coloured lines on top of different coloured regions, and we've got various rules. So likewise, if we've got a white line on top of a white region, then we'll have to make that white line a little bit darker. We'll make it grey so that it becomes visible. And if we do that, then you can get this inversion effect shown here. So here's the floor. It's quite dark, so it's turned out to be a dark region. But we also want to draw these dark lines. So they're now drawn as grey. And although it's inverted, it still sort of visually, aesthetically makes sense. So we can keep as much information, as much detail as possible by doing this. So that's our basic approach, but we can, of course, play around with it. And here's one example inspired by Matisse with his very patterned sorts of images. I showed you already an example where we can apply some patterns to these regions that we've pulled out. That's sometimes more successful than others, because, of course, the trouble is you've now got a bit of a sort of conflict between the features inside this region and the pattern, and sometimes it can be rather hard to actually make out the features, the lines. So this is not always successful. We did try a few ways to improve it, but never quite managed to crack it. And then we've got this idea of simplifying these regions, these tonal blocks as we call them. And again, we can fit, like with the Art of Shapes work with Song, we can fit geometric primitives just to give that extra degree of stylization. So I fitted here some parallelograms and some ellipses and some triangles. Now, we said we want to keep the rendering nice and minimal, so we only have 3 intensities, black, white, and grey. But if we do want to have a little bit more, then we can do a sort of multi-resolution approach. So here, I've processed this image at 3 different scales. So we've got a coarse version over here, going down to a fine version over here. And then if we just literally average them all together, then what we can get is something that combines all of them. We've now got, I think it's 12 different tones. So now we have more tones, so it's not quite so minimal, but it's, in a sense, more robust and a more detailed rendering. So again, artistically, you may prefer one or the other. So it looks quite realistic in a sense, but of course it has been simplified quite substantially. There's all sorts of details that have been removed. The face is mostly quite flat and so on. So although it's realistic, it's also heavily stylized and abstracted. Right. What time am I meant to finish?
I think it's about 5 minutes for a question, should be all right. So
Right, okay.
yes.
I'll maybe go through some of this quite quickly. We've got some more bits at the end. So one of the problems is that sometimes when you have an image to process, there's so much structure in the image that you end up with a rendering that looks like this, where it's very hard to actually see the object of interest. You know, the rendering program doesn't know that all these stones in the wall aren't really as interesting as my son who's coming through a hole there. And you get something like this, which is just visually impenetrable. So we spent a fair bit of time trying to improve this, again using some standard computer vision techniques. And I'll go through them relatively quickly. But what we did was we started off using salience. Now, salience, for whatever reason, has become a hot topic in the last 5 or so years. And there are literally hundreds of papers that are coming out on different techniques for detecting salience. And so the idea is you just feed in your image, and out comes a salient snap that tells you which bits of the image are more important than others. What's quite curious is if you look at, here are 6 arbitrary algorithms, you can see that they're all quite different, so they can't all be right. And in fact, I would say they're all wrong. So that's the problem, that although we hoped to use this salience to determine what was relevant and what wasn't, it didn't really work terribly well. Well, anyway, I've also written a paper on salience. There's my one over here. So I thought, well, I might as well use that one. And then once we had that, we can then use that salience map to vary essentially something between the foreground and the background. And so you can see here are some results here, but it's not really quite doing the job. I say we had a play with various other techniques. So as I say, trying to do it automatically using salience is somewhat error prone. Here was another approach using a semi-automatic technique. So the idea is that you'd use scribbles. Now, in computer vision, somehow it's anathema to have any user interaction. But in computer graphics, that's absolutely fine. So we went down that route, and we drew some scribbles in the image. So these are the green and the red lines here that the user draws in the image. Green was signifying an example. So the green has to go through the foreground object, and the red goes through the background object. It doesn't have to be precisely anywhere, as long as it's in the background and in the foreground. And then using this supervised watershed segmentation, we get this here. It just builds a model of the foreground from examples of the colors under the green line, and it builds a model of the background likewise from pixels in the red. Using these 2 models, it then assigns a pixel to one of the 2 classes. It's not exactly perfect, of course, but we can then refine that initial segmentation using grab cut again. And you can see, apart from the missing hand, it's done a pretty good job. It's got the boundaries quite precise. It's got the right shape. And then we can now use that to modify the image in various ways. Well, the first approach we thought was, let's just reduce the contrast in the background, and then when we run our line detection and so on, it won't find so much in the background. It will be suppressing the background. So the way we did that was to do some essentially Poisson domain editing. So what you do is you essentially just apply an edge detector to this image here, and then we reduced the edge magnitudes in the background, and then we did a Poisson reconstruction of the image from the edge map, which gave us this. So this is after the editing to reduce the contrast in the background. But as you can see, the results, although the foreground is clearer, I guess artistically it doesn't really look quite right. And we tried various other approaches. Here we're doing some blurring, a bit better. Here we're doing some rescaling, maybe. But anyway, let's jump on to the next bit, which was we said that we could stylize our regions by fitting geometric models to them. So we've got lots of possible geometric models, triangles, rectangles, parallelograms, you name it. The question is, which ones should we use? So what we thought we could do is maybe try to automatically select the appropriate region. And we use this thing here, the Bayesian information criterion, which essentially measures the quality of a model fit. So this is a standard technique, not from computer vision, but it's used in lots of different domains. And essentially, you're just measuring the quality of fit in terms of the residuals of the model fitted to the data, plus a penalty here in terms of the model complexity. Because obviously, if you've got a very highly parameterized model, then you can overfit, and you can drive down your residuals to 0. So we have this term here, which is penalizing overly complex models. And if we use this BIC criterion, then this is what we get. And you know, it's quite nice, seems quite appropriate, and the nice thing is it's totally automatic. Well, someone pointed out that our images, the results, sometimes looked a little bit strange because we have some double edges, or double lines rather. You can see here we've got black lines adjacent to white lines in many different places. Sometimes we have only black lines, sometimes only white lines, but quite often we've got these double black and white. So when we went back to think about it, we realized that this paper was using the Laplacian Gaussian, or difference of Gaussian, as a line detector, and it gives a high response when there's a line, but also, the thing is, there's also a response when there's an edge. In fact, of course, we know from Mar's work on edge detection, the Laplacian Gaussian is ideal as an edge detector if we just look for 0 crossings. So here's a 1D signal here, and if we apply the Laplacian Gaussian, we get this shape here. 0 crossing is centered on the edge here, and on the dip, on the minimum there, which corresponds to a dark line in the image, then we get a peak in the Laplacian Gaussian, and we get a minimum for the bright line. So we're getting these spurious responses here, either side, minimum and maximum, either side of an edge, which is why we get these bright and dark lines. So what we came up with was a little scheme where we used just the first derivative of the Gaussian to also detect these edges, and then suppress the Laplacian Gaussian responses so that we could get rid of these double lines. So this is our first derivative of the Gaussian, which we just use as a mask to suppress the lines. And so if we start off with this, then with the suppression, we can end up with something like this. It's a little bit noisy. We could also tidy that up if necessary. Or a second approach was using the heuristic that humans use, which is that the sun illumination is above. Yeah, so if we assume that, then what we know is that we have shadows underneath objects, but we don't have highlights underneath objects. So it doesn't make sense for a bright line to be under a dark line, because if the sun was above shining down, it just wouldn't happen. So we can suppress bright lines under dark lines, and again, we can get also quite nice cleaned up results. Okay, well, I'll better go through somewhat quickly here. So I'll just skip over some of the details here, just to say there's lots of things you can do to improve this pipeline. So for instance, here, if we get a result, you might think it doesn't look that nice because the face has gone all dark. But of course, we can use our tools from computer vision to do some face detection. So here, using OpenCV, we've detected a face, but it's a little bit rough and ready. So if we combine it with skin detection and just combine these two, we can actually get quite a good mask, which tells us where the face is. And then on that face, we can suppress this dark region and say that faces should be not black, not white. They should just be mid-range color, and it looks rather nice in that way. We can also do some eye detection, which could be handy. And the reason is this: if I start off with this image here of my kids, detect my lines, detect my regions, use my rules to combine them together that I told you about before. Before we do that, we refine the initial edges with the grab cut. Now, do you remember I said that grab cut can change the topology of the regions? So it's actually done a good job there. It started off with that, and it's realized that these eyes are dark and therefore should also be labeled black. But the problem is now when I combine together my regions and my lines, I'm trying to draw a black line on top of a black region. I've got the rule which says recolor it as gray, and that's what I get. So it looks a little bit scary. So what we can do is, again, do some face detection, followed by eye detection, and say where there's an eye, don't apply that rule. Okay, we can apply a different rule to make sure that black lines stay black. So it sounds like a little bit of a hack, all these sort of things, But the thing is, as humans, we're very sensitive to errors on the face. So it's worth a while adding some of this extra processing to make sure that faces are done correctly. Okay, so there we go. There's our rendering. This is a two-tone version without the grays. And again, as I said, the idea was that this should be able to reliably generate renderings that are recognizable. So hopefully you can recognize all these individuals there. They're all famous people, just in case you can't. There are the photographs that we use to generate them all. We can generate color. I'll just skip over that. We can add some gray level information to make it a little bit less non-photorealistic, to make it a little bit more realistic. So if you want a sort of halfway house. And let me just finish off then with evaluation, because evaluation is obviously very important. How do you evaluate a non-photorealistic rendering style? Well, there's still quite a debate about that, but we followed this paradigm that a few people have used, which is to place it in a game. And the idea is, some of you will have seen this game where you've got some tiles, and you can just turn over a couple of tiles at a time. And if the two tiles are the same, then you can just click on the two, and they'll stay turned over. So they aren't the same. So let's do another two. And what you have to do is remember where the tiles are, so that even once they're covered over again, you can still remember where they are. And if a new one gets uncovered, you can click on the two and keep them turned over. So the question is, how fast can you solve this game? Or how many key clicks do you need to use to solve the game? And so what we thought was, if you've got a good rendering style, it should facilitate your memory, that you should be able to remember where these tiles are. So what we had was, we had a version where we've rendered these tiles in different NPR styles. We've got the original photograph, we've got a very highly stylized mosaic version, and we've got an artist's renderings. An artist actually drew pictures of all these people. This is in the Surrey XMTV dataset. We've got our own rendering style there, and so on. So what we did is we ran this experiment with some 100-odd people, and once we measured, and we had different versions of our algorithm, the basic one, the pyramid one, we've got the artist's rendering style, we've got the mosaic, and we measured the time to take to complete, and what we showed was that there was no statistically significant difference between our rendering and the artist's rendering. So essentially it said that our method captures the salient detail that is necessary to be able to recognize the image. So it's not totally evaluating it in terms of, it's not actually looking at the aesthetic, artistic qualities of the image, but at least it's showing that there's some merit in this style in terms of its fidelity. And just to finish off, I'm not going to do any big conclusions, but just to finish off, if you go on my webpage, there is actually a demo there where you can upload your images and try it, a bunch of the methods that I've talked about today. Thank you.